All right, this chapter we're going to be looking at matter, which, at least at the beginning of this chapter, is very similar to what we've all learned back in elementary school. So matter is the stuff the universe is made of. It's something that takes up space, and it is how we go about classifying things. It's our basic way of classifying. All right, so we are going to be able to classify these by their properties and how we can observe and how we can interact with them, and so forth. And we're going to see that our physical states of matter are the exact same thing we've kind of always known. They're solid, liquid, and gas. And we have our little Erlenmeyer flask to demonstrate those differences. Solids actually take up have their own shape based on the type of material they are. If you get a liquid, it'll expand to that container, but of course it doesn't fill it, and then gas actually fills up both the entire container and spreads out throughout. And we also know we can change most materials to the different states of the different physical states by changing temperature. All right, so properties that we're going to talk about with our matter are physical and chemical in nature. Now, physical properties are things just like the physical state, solid, liquid, and gas, and the fact that we can change from one to the other just by changing temperature is a physical property. The other physical properties that we know of are color, odor, taste, boiling point, melting point, and one that you might not be fully familiar with, density, which we introduced last chapter, was mass over volume. That is just a physical property. And then chemical properties are ones that change the substance. So if it is no longer exactly like the same thing it was, then that's a chemical property. So burning, for instance, is changing the material. You can't undo that. Same with rusting. It'd be nice if you could undo rusting, but we really can't. So we can typically tell the difference between a physical property and a chemical property by simply asking, can you undo it? All right. We're going to look at some of these, but that was what the key thing is to look at whether or not you can undo it. So we're going to look at some examples of various different things and ask if they're physical or chemical changes. All right, so the color of copper sulfate, is blue. Interesting, because copper, has got a copper color. Copper sulfate, turns out it's blue. But it is just a definition of a color. That is a physical property. Melting of snow. Got to be physical simply because it is a temperature change. It's something to do with temperature. Same with the next one. Melting point of sodium metal is 97.8. That is a physical property. The metal of gold is yellow. Dealing with color, it's physical. Stretching of a rubber band. Theoretically, you stretch it, you let go, it goes right back to being the same rubber band. That is just a physical. Technically, even if you break it, even though you can't really undo that, you haven't changed the nature of what that rubber band is. It's still just a physical change. All right, here's our first chemical change. Aluminum generates a colorless, odorless gas when added into H2SO4. Well, aluminum, being a metal, H2SO4 is a solution. If we have a gas coming off, that's got to be a chemical change. And technically, the gas that's coming off is actually hydrogen gas. Sodium metal is so soft it can be cut with a knife. Even though it makes a new material, as in you can't really undo that cutting with a knife, it is still just two pieces of sodium. It's just smaller. Chromium does not rust. All right, it's still chromium. It didn't go through a chemical change, though. That is actually a weird chemical property. The resistance of it rusting is a chemical property because it would have made a new material, which is the rusted chromium. Next one, perspiration evaporates when you relax after jogging. Well, it is just water vapor evaporating. That's a physical property. Cornstalk grows from a seed. Chemical change because it's actually all that comes from that little tiny seed. Table salt dissolves in water. That is actually a physical property, because we can undo that. If you actually take salt and boil away the water, or salt water and boil away the water, you'll have salt. Gasoline is flammable, definitely a chemical change. It's going to turn into carbon dioxide and water as it burns. And last one, nitrogen freezes at negative 210 degrees. That's something to do with temperature, like these up here. That is a physical property. All right, stop and think about this one for a second. A nail rusting, chemical or physical? Yeah, it's a chemical change because the nail is oxidizing, it's gaining oxygen, it's turning into a reddish brown material. That is definitely something new. All right, on to classifications of matter. We got our three phases, but how are we going to find it? We don't always find it as like water is found multiple ways in our day-to-day life. We find it as something we drink, but we typically have it mixed with other things. And whatnot. So we're going to classify matter as two main categories, just whether or not it's pure or mixtures. We're going to find we don't often see metal or anything really as a pure substances. I was mentioning metal because most metals we find are alloys. They're mixtures of more than one type of metal to get the best behavior out of each of them. So we get mixtures way more often. All right, so pure substances have this as their consistency. So constant composition, and they're homogeneous. All right. So what do we mean by that constant composition? Well, it just simply means that they all have the same composition. No matter where we isolate that particular pure substance, it's going to be exactly the same. Now, one metal we can find pure often is actually copper. Now, even though a penny is not pure copper, the outside is pretty much pure copper. You can typically, in many cases, see on the edge where it's coming off, especially if it's been circulated well enough. But the outer part of a penny is typically nothing but pure copper. Now, we don't see pure metals often. I mean, steel is not really found on the periodic table. It's mostly iron. But pure iron rusts really, really fast, and it doesn't have all the most ideal properties, so it's typically mixed with other things. And you mix the right things, you make things like stainless steel, which has more chromium in it and such. But we get mixtures of most metals. Even aluminum from like aluminum cans, it's not fair to say it's a pure substance either, and that's simply because the outer part of aluminum actually oxidizes relatively fast and forms a very thin layer of aluminum oxide. It's only about a few atoms or a few few atoms thick of aluminum oxide, and it keeps the rest of it from oxidizing, but it's not really right to call it a pure substance. All right, but when it is pure, we're going to use this word homogeneous, which means it has a uniform, it's uniform throughout. So if you cut into it, it's still the exact same pure substance all the way through. And if it is a pure substance, it cannot be separated to components by physical properties. And what I mean by that, if it is that pure penny, if I heat it up and liquefy it and then let it cool back down, it'll be the exact same pure copper. All right. When we find a pure thing, we're going to find it as either elements or compounds. Now, elements, we don't find too many pure elements in nature all by themselves. The ones we do find actually kind of easy and that will stay kind of pure are gold, silver, and to a degree carbon. The pencil lead, if you have a pencil, it's made out of graphite, that is almost nothing but pure carbon. It's not a very hard substance, breaks and falls apart relatively simple, but it can be found relatively pure. The compounds are where we find most or more of our pure substances. So water, for instance, H2O, while we find it very close to pure in many cases, it turns out even our drinking water is not super pure. And if you were to go to some place like Walmart or Publix and buy distilled water and tasted it, you'd find it tastes very different than what you would consider water. And that's because most of the water we have in contact has small amounts of salts and such in it, which we find tastes normal. So that's why it's safe to say we don't really get pure water very often. But you can drink distilled water. It's not dangerous. It would be dangerous to drink it in excess because it is pulling, it's going to cause your body to give up the minerals to the water itself. So it actually de-electrolytes you. So it does the exact opposite of what maybe Gatorade does. All right, so that's our compounds. Two or more elements chemically combined to make a new compound. All right, the law of definite proportions has some rules on that. Turns out that if I am talking about water, which we have a chemical formula of H2O, it does actually mean that there is definitely 2 hydrogens for every 1 oxygen. If we somehow change that, we make a new compound. Like for instance, H2O is drastically different than H2O2. H2O2 is hydrogen peroxide. You wouldn't want to drink that even small amounts. Properties of compounds are never related to the properties of the elements. They might be similar, but they are not the same. We're going to see that some more on the next slide. And compounds can't be broken down into elements through physical means. We actually can do that through chemical reactions, but not through physical means. All right. That second bullet point down there, the properties of compounds not related to the properties of the elements. Let's look at this one. Now, the last picture here is something you're very familiar with, sodium chloride, table salt. Not a very dangerous substance. We actually have day-to-day you come in contact with it on a daily basis. Has a melting point of 800 degrees Celsius. It's going to be a solid on almost every situation you can think of. There's not many people that have access to a stove that could get hot enough to melt, let alone boil salt. Does dissolve very easily in water. Has a very predictable density. We all know what it looks like. It's got a white color to it, or crystalline cover if you look colorless if you look close enough. Yet, sodium chloride is actually made out of sodium and chlorine. And what we have here is pictures of those two other components. Now, chlorine gas is about the only one of these two you've probably come in contact for any length of time. And I say that simply because we all have been around pools here in Florida that have chlorine possibly too high in them. I mean, you can feel that. It burns your eyes just walking near the pool, or you can smell it at least. Well, this container here being yellow, that would be a very concentrated amount of chlorine. We normally don't see any color to chlorine because it's in small trace amounts. But if it is dense enough, this is actually a very dangerous container, because if that were to open near you, you'd get that burning sensation you get in your eyes when a pool has too much chlorine. You get it almost immediately. All right, next to it is sodium. Now, in this picture, it's showing the person cutting it with a butter knife, and that really is the case. Sodium is a pretty crappy metal with regard to strength. It does actually cut that easy. A butter knife can easily cut through sodium. Now, if I did have some as a demonstration, you'd almost need to do that to show you that it is metal underneath, because sodium actually reacts very easily with moisture in the air, and the whole outside of it will be either white or black, as it's depending on what stage of oxidation it is in. Like at our chemistry lab, our sodium actually looks more like a snowball because of the amount of oxides that are all over the outside of it. But drastically different properties than sodium chloride. I mean, look at these melting points. The average of this is right around 0 degrees Celsius, nowhere near what sodium chloride gets to be. So it turns out the properties of the compound made by the elements is totally different and not related at all to the individual components of it. Something else interesting, if you want to see something kind of cool, bring up YouTube and look up throwing sodium into water. You'll see it reacts very violently with water, and that's simply because it's rapidly reacting and causes the water to give up hydrogen, which is why in some videos you see it looks like it catches on fire. All right. Oh, that's that same slide. we're on to a different type of chemical process. So that last line did say that you can't break compounds down into elements. That's what physical means. Turns out chemical means we can. Matter of fact, water can be turned into hydrogen and oxygen by running electrical current through it. And that's what they're showing in this little picture. This is electrolysis. By running the electrical current through it, we generate oxygen on one side and hydrogen on the other. And if you notice, doesn't it look like the volume here is like half what this side is? And that's simply because every water molecule, if we take two of them, we're going to make two hydrogen molecules and one oxygen. We balance all that equation. So you do make twice the volume of hydrogen compared to oxygen. All right, on to mixtures. Our mixtures are actually just substances that can be separated through physical means. Now, a great example of a mixture would just be salt water. Now, the reason I say it's a great mixture, that salt water does have different properties than regular water. You would know the obvious one would be taste. You could definitely tell the difference between salt water and regular water. And the smell even to a degree. If you go to the ocean, you can smell the salt water. But it turns out if you were to take a sample of that salt water and heat it up, you could actually boil off the water, or at least evaporate off the water, and you'd be left with a salt residue. So you can actually separate those just by actually doing a physical change, heating it up. Other ones that pay off are different type of separation. There's distillation, there's filtration, there's centrifuge. We'll talk about these all some. Filtration, that really is just like a coffee filter. So if my mixture we're talking about is muddy water, a coffee filter could do wonders to separate that out. It could actually separate out most of that dirt. Centrifuge is actually going to be a little bit more beneficial to speed up the process. Centrifuge really is just a spinning disc, and you can put like test tubes in it, and as they spin, they speed up how fast things settle out. All right, so got this picture to talk about some of our mixtures and what we're talking about. Now, I'm pretty sure I got my labels backwards here because most of you know that if you put table salt in water and stir it really well, you can dissolve that, and you would get something more clear looking. Yet, if you were to put sand in there and mix it up, you might actually look uniform if you spin it fast enough, but as soon as you stop swirling that, obviously the sand would settle out. And that's what I think. I think this is the sand picture, and this is the table salt. And it would be clear that they're mixtures, at least with regard to that sand, because even if I'm spinning it fast enough, as soon as I stop spinning it, you're going to definitely see that separating out. Can't really see that too easily with salt water. All right, but if I were to take that salt water and do some distillation, I can separate them out. And that's what they're demonstrating here. So we got a sample of salt water here. And what we're going to do is heat it up with a Bunsen burner, bring it up to a boil, and turn that water into steam. We can condense that through this little condensing tube. You notice that it's what they're trying to show here is this is a glass tube going through the middle, but it's got another glass tube on the outside of it, and we're going to pump water through there. It's just some cool water to get that steam to condense. So over here, that pure water drips out, leaves the salt behind. And that's what they're showing here. When it's all done, we have the separated salt and we have the pure water. That's the whole idea of distillation. It doesn't typically work this beautifully in the sense that you don't get this nice little pile, because if you think about this, as this gets less and less, that salt's going to build up, create little cavities in there, and that water gets steam up, and so the salt's going to get coated all over the sides. It's not going to form that nice powder. Okay, our mixtures can be separated in just two heterogeneous and homogeneous mixtures. Heterogeneous meaning you can tell the difference. There's our sand and water mixture, oil and vinegar, salad dressing. Yeah, you can stir all those up maybe to the point where you couldn't tell they're two separate. So, but as soon as you stop actually disturbing that vessel, it's going to be immediately noticeable that it's a mixture. That's the difference on heterogeneous and homogeneous. Homogeneous mixtures, even after you stop stirring them, they will look uniform throughout. They say sugar water, but a lot more obvious maybe Gatorade. If you take a mixture of Gatorade and put it in water and stir it up and mix it, it's definitely going to look homogeneous because it's distributed throughout. And there's nothing you can do to get that to come back out under normal conditions. It's going to stay that mixture all by itself. Now, other ones we come in contact with day-to-day basis, gasoline. Turns out that is a mixture, has as many as 30 components in most cases. Air around us, it's mostly nitrogen and oxygen, but here in Florida there's also a lot of water vapor. There's carbon dioxide, there's other compounds. So there's a lot of stuff mixed in with our air. And almost every metal alloy you come in contact with a day-to-day basis is a mixture of different elements to give different properties. Okay, the difference between mixtures and compounds can be split into these nice little categories. Now, this is just a really summary of what we've talked about. So, mixtures, the components can be separated by physical techniques. Compounds, they cannot, not by physical techniques. The mixtures have a variable composition. Compounds, the composition is fixed. Mixtures' properties are related to those of its components. Salt water has a similar boiling point to water. But compounds, those properties are not necessarily like those. If they are, it's really just a coincidence. Mixtures, little heat is produced during the formation. There are certain kinds where we take advantage of that. If you've ever been in contact with instant cold packs or instant hot packs, they are mixtures that produce heat when they mix, but they're typically doing a chemical change when that happens. In compounds, there is considerable heat being produced or consumed in some cases. But combustion's a great example of that. When you burn gas, it actually releases a huge amount of heat. Okay, separation on our physical properties, the separation is typically done by just a few categories. So boiling point can be used to separate from distillation. So if we have two substances have drastically different boiling points, distillation will normally separate them out. That is actually how we separate alcohol, ethanol, from water and straight distillation. You typically can't get it super pure, but that is kind of the difference between beer and liquor, is how much they've distilled out the water. All right, the size of the particles, sand and water, coffee and water. Typically, if the size of the particle is drastically enough, you can separate through filtration. And even a coffee filter is actually adequate in many cases. Now, this next one's adherence to a surface. That's an interesting one. So chromatography we can use to separate things out. Now, think of chromatography as maybe a coffee filter. And what we could do on this to demonstrate it, we're just actually imagining we put a little line on here, and we're going to put a dot of ink on here, a dot of a different color ink here, and a dot of different color ink here. Matter of fact, I can do that, can't I? Yeah. And what we'd find, if I did this with the right type of marker, put this down into a solution of maybe like gasoline. As the gasoline gets pulled up in there, it will actually pull these inks with them, and you will find that the inks don't necessarily move at the same rate. And that's because the different color inks stick to the paper differently in many cases, and they'll separate out. Matter of fact, you don't see it too much anymore because we got much better inks than we did. But if you go back just 20 years ago, red ink and brown ink and mini inks were made up of different pigments, and they would separate out different colors. So that green, you might actually see later on a blue dot up there and then a yellow dot down below, where the pigments got separated as they pulled up. Nowadays, with nitrogen-based dyes, we don't see that too often. Almost all of them are single pigments anymore. Makes it cheaper to make, and you don't get that weird separation when you get them exposed to something even as simple as gasoline. But chromatography comes in handy to identify things in chemistry, especially mixtures. All right, so we're going to try to identify these as pure substances or mixtures. And if they're mixtures, we want to try to identify if it's heterogeneous or homogeneous. All right, so the first one being copper, that's got to be an element. So it's a pure substance. I am going to put element. Let me change back to black so we can see that. Diamond. Well, turns out it is a pure element. It is just carbon. It's actually a complex of carbon. Sulfur trioxide. That's a compound. Has one sulfur for every 3 oxygens. Dirt. Turns out that's a mixture. It's got a lot of things in there, some organic material and minerals in it. Drinking water. For the most part, it's a mixture as well. It's mostly water, probably 99% water, but there's going to be some other minerals in there that gives it the taste that we're used to, especially on drinking water. Chlorine. Probably safe to call that an element. Actually, not an element, a compound, because chlorine is actually Cl2 most of the time. A nickel coin. Turns out these are now mixtures. The outer part is mostly pure nickel, but the inside will be probably likely zinc or some other cheaper metal. It turns out nickel itself is kind of expensive. Italian dressing. If you're not aware, most Italian dressings are actually mixtures, and they are heterogeneous mixtures. And then we say that because it's actually kind of obvious if you look at Italian dressing that it's a mixture because there's things floating in it. Now, the drinking water is definitely a homogeneous mixture. Nickel coin, probably safe to say homogeneous because you can't easily tell looking at that it's an alloy. Right. Aluminum foil, next one up here. Probably safe to say that's an element. There is going to be some aluminum oxide on the outside, but you are typically seeing right through that. That's as close to a pure substance as we see on aluminum. Tea. Now, tea can look like a homogeneous mixture, but this one actually says ice with a lemon slice too. So that's definitely a mixture, and it's definitely heterogeneous because I don't know of anybody who couldn't tell the difference between ice, a lemon slice, and a liquid. Carbon dioxide, compound. Water and motor oil. Oh, that'd be a scary thought, right? Having water inside your car with motor oil or having motor oil floating around in the ocean. Those are definitely a mixture, and it would definitely be heterogeneous. There's no way those would mix. Mercury in the thermometer. That's actually an element. Mercury itself is a metal. It just happens to be a liquid at room temperature. How about ice? Now, it's a compound. It is water. It's just in the solid form. Human body. Definitely a mixture. Definitely heterogeneous. And then last one on here, baking soda. For the most part, that is a compound. Now, baking soda we get at the stores probably got some impurities in it, but for the most part, it is relatively pure baking soda. All right, number 2, how would we separate a mixture of dirt, salt, and water into 3 separate components? Well, if we think about it as a container with all 3 in it, so I'm going to write it as salt, dirt, and water, we could probably separate out the dirt with just a filter. So that's representing a filter paper. We're going to put it in a funnel. And if we do that, the dirt would stay up here and the salt and water would come out. That makes sense because the salt has dissolved in the water. This is now salt water. The dirt stays behind. And then if I wanted to separate the salt and water, go back a couple slides. We have that distillation apparatus where we're going to heat up that flask with a Bunsen burner. The vapors come up here and we can do that little condensing tube. And we have the pure water over here, and only the thing that we left behind here was salt. So a little distillation. So filtration and distillation, we could separate those into 3 components. Okay, And we had that already. So, review of this. We can separate our matter into elements and compounds, if it's a pure substance. Mixtures are homogeneous and heterogeneous. So, salt water. What type of mixture is it? Well, if we're talking about ocean water, it's probably going to be heterogeneous because you'd probably see stuff floating around in there. But if it is just salt water, it's going to look mostly like water, and we'd know it's salt water mainly by its taste, maybe from its smell. But it's probably safe to say that salt water is a homogeneous mixture because it probably would look uniform throughout. How about Italian dressing? That is definitely a heterogeneous mixture because salad dressings, almost all salad dressings, you can actually see the individual components or some of the individual components in there. Gives it some texture. And that gets us done with Chapter 3.